My name is Charles Edler. Welcome to my Physics 2 Lab 4 bar magnets. For the intro, the purpose of the lab was to examine the effect of magnetic dipoles, understand the distance relationship for magnetic strength, and find the magnetic dipole moment using Biot-Savart law. For the results, we found that the magnetic field of the bar is proportional to distance, which is magnetic field is proportional to the distance, the negative third. And we found the dipole moment value being 1.53 amp meters squared. And on the right, we can just see that the field lines, it goes from north to south for bar magnets. So concepts we need to know, Biot-Savart law, which is a fundamental principle in electromagnetism that describes a magnetic field generated by a constant electric current. And the equation we'll be using is based off the magnetic field of a dipole on axis, which is mu naught over 4 pi times 2 mu over z cubed or r cubed in our case, and mu is equal to a area times current. And with that, we can derive the equation of distance dependence, which is the ln of the magnetic field is equal to the ln of k, which is all the constants, plus n, which is the power that r is, so -3 in this case, and then the ln of the distance. So the setup for the lab, we had to download an app on our phone that can access the magnets within our phone, and then using the values in the app and a bar magnet to find the sensor of the sensor, like you see on the right. And the system we'll be using was the bar magnet and surroundings with everything else producing a magnetic field around our experiment. Then now for the experiment, on the left we have a graph that measures that used a magnetometer readings and distance of the readings. And on the right, we can see a plot of data of those readings in ln form. And we can see that there is a slope of negative 2.7805, and the y-intercept was negative 17.27 if you follow the linear line going down. And with those values said before, we can calculate the dipole moment with r being the slope of the graph and your ln of k being the y-intercept of the graph. And since we know the magnetic field of the bar is equal to k r to the n, and the on-axis dipole magnetic field is equal to what I said before, mu naught times 2 mu over r cubed divided by 4 pi. We can set those equal to each other, and we find that mu equals 1.53 amps meters squared after substituting at the end. Some errors and assumptions we have to make for the lab. Some errors would be other magnetic fields in the surroundings, like other computers or other phones, affecting the magnetism of the bar, and also an inaccurate location of the phone sensor. Like if we were misreading where to put the sensor in the first place, that can affect our values for the dipole moment and everything else we did in the lab. However, there's some assumptions we had to make during the lab, like acting as the bar magnet was a perfect dipole, along with assuming that the magnetic field is zero at a far enough distance. Now, some what ifs. What if you had oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, my results would have become less accurate because Earth's magnetic field magnitude would have interfered with the bar magnet's field and caused inaccurate data to be measured, and we'll have to use some other form of measurement to get the correct value. And then what if you were to stick two magnets together end to end and run the experiment again? How would you expect your measurements to differ? And I would expect the n value, the distance dependence, to remain the same, just as it was -3, which is actually in the on-axis theorem. And by my calculated, a magnetic dipole would have increased because of the increase in strength of the magnet. Thank you.